Hello everybody, in this video we will prove that tau xy equals tau yx. Tau xy equals tau yx. So what's tau xy and tau yx at first? So let me show you this 3D element. So this is a small rectangular parallel piped element, and where this element is parallel with this one is parallel with this one, and the all opposite sides are equal. So let's call this A, the side from here up to here A, and from here up to here let's call it B, and the third dimension is from here up to here, let's call it C. So shear stress, this is a shear stress, tau represents the shear stress. So we have here two subscripts, x and y. So this means the first subscript describes the direction of the plane. For example, this plane, we know that planes are represented by their normal vector. So this plane, for example, has a normal in this direction. So this plane is in the x direction. Okay, so this plane has a normal in this direction, in the y direction. So this plane is in the y direction. In the same way, for example, this plane and the back one, this plane is in the z direction. So the first subscript describes the direction of the plane. Now shear stresses act parallelly to the area. Okay, so they are parallel to the area. So let's have here a shear, and in the same way at the top surface we have another shear, and opposite to this one we have a shear in the opposite direction, and opposite to this one we will have shear at the bottom surface. Now this shear is acting in the x plane, so we will write the first subscript. The second one, this one shows the direction of this shear. So the direction is in which direction? In the y direction. So this shear is called shear tau xy. It's acting on the x plane in the y direction. In the same way, this shear is acting, let's write the shear. This shear is acting in the y plane. This is the y plane. So we will say tau y. It's acting in the x direction. So it is tau yx. In the same way, if you come here, it is tau xy, and at the bottom it is tau yx. So here, if we want to calculate the force on this face and on this face and the left side face and on the bottom face, we have this. The force on this face, let's call it Fxy, equals the shear stress tau xy times the area. This area is what? It is C times B. So it is C times B. Let's consider the top surface. So let's call this one, the force on the top surface, Fyx. This will be equal to the shear stress tau yx times the area. This area is what? The distance from here up to here, it is C, and the distance from here up to here, it is A. So it is equal to C times A. In the same way, the shear here is tau xy times this area equals this area, so it will be similar to this one. And the bottom surface, the force on the bottom surface will be similar to this one. So now let's go to a plane stress condition. However, before that, we have to know that the z-axis is neglected in the plane stress condition, so we will have only a two-dimensional element, something like this. Okay, something like this, a two-dimensional element, something like this, and you have x in this direction and y in this direction. The distance from here up to here, it is similar to this one, it is a, and the distance from here up to here, it is b. Okay, so now let's go to the 2D plane. So here we have this 2D element like this, and do not forget about the forces acting on the faces. Here we know that there is the force acting on this face is Fxy, and the force acting on the top one is Fyx, and at the bottom Fyx, and at the left side Fxy. So these forces will be applied on these two-dimensional elements like this. Okay, so here we will have a force that's upward like this, that is Fxy, that's equal to tau xy multiplied by c times b. And here there is a force here, shear stress times the area. So here you will have a force on the top surface, that is Fyx, that's equal to tau yx times c times a, or a times c. And in the same way, the opposite of this one is acting here on the left face, here on the left face. So here you will have similar to this one, Fxy, this will be equal to tau xy times b times c, similar to this one. And the opposite of this one is in the bottom face, it is Fyx equal to tau yx times a times c. Now if you take a moment at this point, about this point, let's consider this as maybe the origin, or if we take, and the dimension from here up to here, we have to know that it is a, here is a, the vertical one is b. Okay, so if we take the moment about this point O, it is automatically this force and this force will pass through this point, so their moment will be 0. So now the only force that will make moment will be this one and this one. So now let's take a moment about O must be equal to 0 for equilibrium, and let's take the counterclockwise as positive. Now this implies that this force multiplied by the perpendicular distance, that is a, it is acting in the counterclockwise, so it is positive. So Fxy, that is equal to this multiplied by this distance. So Fxy multiplied by this distance is a, the perpendicular distance. Okay, and this force is acting in the clockwise direction. The moment will be in the clockwise direction, so it will be minus Fyx times the distance, the perpendicular distance is from here up to here, it is b. This must be equal to 0. This implies, if we take this to the other side and substitute Fxy equals this one, Fyx equal to this one, then we will have tau xy times the area is c times b times this distance a. If we take this to the other side, equal to Fyx is tau yx times a times c times this dimension b. Now here you see cba and here acb. This element will be cancelled out with this one, So what we have here is tau xy equals tau yx. So it is now proved. This is all for this video. Until next video, goodbye. See you next time.